Welcome to the fascinating world of quantum-grounded predictive AI architectures. Today, we explore a theoretical paper that proposes a groundbreaking fusion of two revolutionary fields: artificial intelligence and quantum computing. The goal is to move beyond traditional AI, which relies on classical data and symbolic representations, and instead develop AI systems that interact directly with reality at the quantum level, the most fundamental layer of the universe. Current AI systems excel at recognizing patterns and making predictions based on vast amounts of classical data. However, they are limited by their reliance on abstract, symbolic representations that approximate reality. This paper argues that such classical AI approaches hit a ceiling because they cannot truly grasp or model the underlying quantum nature of the world, where the fundamental rules of physics operate. The authors introduce the concept of quantum-grounded representations. Unlike classical AI, which compresses data into vectors or numerical summaries, quantum-grounded representations are actual quantum states. These states correspond directly to physical systems and preserve quantum properties such as superposition, the ability to be in multiple states simultaneously, and entanglement, the mysterious connection between particles regardless of distance. This direct link to quantum reality could enable AI to capture a much richer and more fundamental layer of information than classical systems ever could. Building on this, the paper proposes the quantum-grounded joint embedding predictive architecture, or QG-JEPA. This architecture adapts a classical AI concept called joint embedding predictive architecture, which learns by predicting one view of data from another to build a deeper understanding. The quantum version elevates this idea into the quantum realm, involving three key components: the quantum encoder, which translates quantum inputs into quantum embeddings; the quantum joint embedding function, which assesses compatibility between different quantum embeddings; and the quantum predictor, which tries to predict one quantum embedding from another. The system learns by improving its predictions to match the actual quantum states it observes, maximizing compatibility with relevant quantum states and minimizing it with irrelevant ones. The paper also explores energy-based quantum world models, inspired by classical energy-based models but operating in Hilbert space, the abstract mathematical space where all quantum states exist. Here, energy functionals define the likelihood or stability of quantum states based on their interaction with the Hamiltonian operator, which encodes the physical laws governing the system. By learning these energy landscapes, the AI effectively internalizes the fundamental physics of the quantum world. To bring theory closer to practice, the authors discuss potential quantum algorithms that could implement these ideas. One such algorithm is quantum amplitude estimation, QAE, which could learn probability amplitudes of quantum states much faster than classical methods, providing a direct and efficient way to represent quantum probabilities within the AI's internal embeddings. For modeling complex quantum energy landscapes, quantum Boltzmann machines, QBMs, are proposed. These quantum-native models could naturally capture entanglement and other non-local quantum phenomena that classical AI struggles with. The Hamiltonians used in these models might include operators representing quantum measurements, biases, couplings, and even quantum tunneling effects, where particles pass through barriers in ways classical physics cannot explain. Causal reasoning in quantum systems is addressed through a modified variational quantum eigensolver, VQE. Traditionally used to find the lowest energy states of molecules, here VQE is adapted to find the ground state of a specially designed causal Hamiltonian. This Hamiltonian encodes potential cause and effect relationships within a quantum system, allowing the AI to map out quantum causal structures by energy minimization. To efficiently explore the vast space of quantum possibilities, quantum walk algorithms are suggested. These algorithms, especially continuous time quantum walks, can speed up search tasks on complex graphs, enabling the AI to navigate the enormous landscape of quantum states much more efficiently. Handling the complexity of quantum data is another challenge. Quantum principal component analysis, QPCA, is introduced as a quantum analog to classical PCA, capable of reducing dimensionality while preserving essential quantum structures. Remarkably, QPCA could be exponentially faster than classical PCA for certain quantum datasets. The paper also touches on quantum approximate optimization algorithms, QAA, for tuning joint embedding functions and quantum generative adversarial networks, QGANs, which could generate new quantum states that mimic real ones. This capability would allow the AI to create internal quantum simulations, effectively running experiments and exploring quantum behaviors within its own quantum sandbox. To illustrate the potential of QG-JEPA, the authors proposed 3 thought experiments. The first is a quantum vision system that processes quantum light, photons, directly rather than classical pixels. This system could outperform classical convolutional neural networks and classical joint embedding predictive architectures in tasks like detecting quantum phases, classifying entangled states, and performing quantum state tomography, thanks to its ability to maintain quantum coherence throughout processing. The second thought experiment involves theoretical causal discovery in quantum systems. Using the causal Hamiltonian and VQE approach, the AI could identify cause and effect links in complex quantum systems with high accuracy, detect non-local quantum correlations, and even uncover quantum contextuality, the dependence of quantum properties on measurement context. The third experiment explores multi-scale quantum classical integration, where the AI learns quantum representations of materials and uses them to predict classical properties such as conductivity or phase transitions. This could lead to breakthroughs in designing new materials, including superconductors, by understanding their quantum foundations. Beyond these experiments, the paper envisions conceptual applications like quantum-grounded robotic manipulation, where robots equipped with quantum sensors and models could manipulate objects at the quantum level, predicting phenomena like quantum tunneling and superposition during tasks such as placing quantum dots precisely. Another application is quantum causal reasoning, where AI could reason about electron interactions in quantum chemistry, exploring counterfactual scenarios enabled by quantum superposition to improve predictions of chemical reactions. Finally, the paper imagines multimodal quantum integration, combining quantum sensory data from light, sound, phonons, and touch, electronic signals, into a coherent quantum representation. Using quantum optimization algorithms, the AI could fuse these data streams while preserving quantum coherence, enabling cross-modal predictions that classical methods cannot achieve. The implications of this work are profound. It suggests a new form of representation where AI's internal states correspond directly to quantum physical reality, potentially solving the long-standing symbol grounding problem in AI philosophy. This quantum grounding could enable AI to represent and understand aspects of reality that classical systems fundamentally cannot. Moreover, the quantum advantage here is not just about speed but about enabling qualitatively new AI capabilities by harnessing quantum phenomena like superposition and entanglement. The paper also emphasizes the importance of physical embodiment, proposing that true intelligence might require hardware operating quantumly to maintain coherence and richer world models, a quantum brain for a quantum reality. However, the challenges are immense. Current quantum hardware is far from capable, with qubits losing coherence too quickly and error rates too high. Realizing quantum-grounded AI would require thousands to millions of stable, error-corrected logical qubits and significant advances in quantum error correction and coherence times. In the nearer term, hybrid approaches combining classical and quantum computing might offer stepping stones. These could leverage classical computers for tasks they handle well while offloading quantum-heavy computations to quantum processors, using variational algorithms like VQE to make progress even with noisy intermediate-scale quantum devices. Energy efficiency is another major hurdle, as maintaining quantum coherence currently demands extremely low temperatures and high energy costs. Research into room temperature quantum computing, topological quantum computing for noise robustness, and more efficient error correction methods is critical. In summary, this paper presents a visionary theoretical framework for a new paradigm in AI, one that directly engages with the quantum fabric of reality. The potential benefits include deeper, more accurate world models, new predictive capabilities, and a fundamental shift in how intelligence is understood and embodied. While the path forward is challenging and long, The promise of quantum-grounded AI opens exciting avenues for future research and technological breakthroughs. Thank you for joining this exploration into the frontier of AI and quantum computing. The journey toward quantum-grounded intelligence may redefine our understanding of both intelligence and reality itself.